hello everyone again to this brand new episode. I am your host, Tim.
And I'm Mikey.
I'm Sahil. Welcome everybody to a brand new exciting episode of Quirkcast. If you haven't already, do join our Discord channel. And if you're watching on YouTube, where we do this at 5 p.m. Pacific, 8 p.m. Eastern, and every Tuesday, then do ask us questions during the episode, and we'll get to them. So, without further ado, Tim, I want to ask you straight up: what is the theory of everything? I already thrown around. What is this?
Yeah, I think this is kind of a culmination of how physics has progressed through the years. We started with Newton's theory of gravity, and slowly, as physics progressed, we have quantum theories, and then we have the theory of electromagnetism. And at each stages, it seems like more and more this seemingly different theories got combined together into greater and greater theories. Then we have the electroweak theory, and now Einstein's theory of gravity. So if we kind of extrapolate a little bit, it feels like inevitably one day, maybe in the future, that we might just ultimately have this one ultimate theory that describes all these this different phenomenon. So that's why there's sort of this feeling of going toward the Holy Grail, kind of the theory of everything in the physics community.
Huh. And so I guess like one question I have about the theory of everything is that what does it mean to like describe everything? Like what is the everything in theory of everything? Is it like subatomic particles, like a reductionist point of view of like understanding, oh, the fundamental constituents, how they behave, or like is it like kind of everything that like us having this conversation with like if you discovered this theory of everything in principle, would it predict that we're having this conversation right now? I pose this to Mikey. I'm gonna just flip the script over here.
I think it's like it goes far beyond subatomic particles because the idea has existed actually long before physics, right? Like I don't know how many thousands of years ago, but people used to think everything was made out of just five elements like earth, wind, fire, wood, or whatever like that was, right? And that was like a theory of everything based on almost no information, just like based on what was present to observers at the time. But that's really an attempt. Like the working hypothesis at the time was that everything we see around us can be just thought of as combinations of these five fundamental constituents, and that turned out to be totally wrong. But people kept on trying to have like Democritus when he posited that everything is made out of these small fundamental individual bits that he called atoms. That was kind of an attempt at a theory of everything. But as Tim mentioned, I think that this idea really started to grow legs um, when it was combined with modern physics um, through Newton, who made the observation that when apples fall from trees and bright lights move across the sky, that these two seemingly unrelated phenomena might have a common explanation. That some force, mysterious force at the time called gravity, just one idea that things with mass attract each other could be responsible for explaining bright stars moving across the sky and simultaneously apples falling from trees. And then, as Tim also mentioned, Maxwell kind of followed up with this that like when lightning strikes and like your magnet sticks to a refrigerator, it's not obvious that there could be a single explanation or single framework for describing both of these phenomenon. But the theory of electromagnetism does indeed explain why magnets stick to your refrigerator, simultaneously explaining why lightning strikes from dark clouds. Um, and so it's just like it's in the last 300 years, as I said, it started to grow legs just from the success, the empirical success of this idea, um, has led to basically, the periodic table of elements, um, which basically describes all of the interactions that we observe around us, including this conversation, right? Including the fact that we breathe air and how that transfers energy to our body through ATP. Like all of this framework can be described through chemistry, which in turn can be described as simple interactions from fundamental particles. culminating in what we now call the standard model of particle physics, which more or less explains everything that we observe with just a simple set of quarks, electrons, and simple interactions.
That makes sense. That makes sense. I guess like so if we kind of like go a little bit like down into it, I guess like if you were to discover a theory of everything, like what would it look like? Like explaining to a layperson, like would it be like an entire book of like one giant equation? Would it be like a one-liner? Like what would it what do we think it would look like? Or how can I conceptualize the theory of everything? I'm gonna go back to Tim on this one.
I think that is probably a bit subjective, and
Mhm.
and maybe it would be nice to bring up an example, right? Like just kind of like when Einstein thought about his theory of general relativity, which is the theory of gravity. In the beginning, everything is kind of really complicated. He wrote down pages and pages of equations. These are highly technical, like nonlinear differential equations that are really pretty much impossible to solve, right? Because he kind of didn't quite understand the mathematics. So it used to be that Einstein's theory had like lines, maybe probably pages of equations describing them, and they all look kind of like disorganized in some ways. But nowadays, if you take a graduate level course in Einstein's theory, you see that his equation is just like, I don't know, 3 to 4 symbols, one line, right? It's because the mathematical maturity of the world kind of caught up to it. So this is what I would expect, kind of the theory of everything, if we have something like it. Like in the beginning, it's gonna look kind of like a jumbled mess. Maybe it will be pages. Maybe it will be a computer program. Just be like, hey, there's like a bazillion terms in some equations. But maybe like, we'll just wait like 100 years, 200 years or something. All that might simplify and get this still down. And I truly believe that that it should. That property has never failed us, right? As we learn more, our understanding of theories get deeper, and they get simplified in some ways. So ultimately, if you ask me what the theory of everything looks like, yeah, it would probably be like some really nice looking one liner, I would say.
Hmm. So that brings me to like another question regarding the theory of everything. So, right now we've talked about like the fundamental constituents, such as like the basic building blocks of matter and energy, and then maybe things such as like even like concepts such as information on previous podcasts and whatnot. But what about explaining like the more kind of emergent phenomenon? So, for example, like atoms make up molecules, molecules make up like biological entities, or sorry, molecules make up chemistry, chemistry leads to biology, then biology leads to like eventually human beings, and then human beings lead to all these like social sciences. So it's like just kind of this like turtles of like emergent phenomenon just going all the way up. And so I'm wondering, would a theory of everything be able to also explain emergence? Like, for instance, if I like look at a flock of birds, and I have this model where like each bird has its own like set of rules of like don't crash into another bird, follow the lead bird and whatever, and then the flock kind of takes on a life of its own. So I'm wondering like how do you guys sort of think about this? Mike, you look intent on this question.
No, I mean, there is a debate, particularly between particle physicists and condensed matter physicists about like reductionism versus emergentism, and it's always kind of confused me. Like, um, I can't think of a single emergent phenomenon that is not predicted by quantum field theory. I don't know, as my advisor used to say, quantum field theory predicts dinosaurs. It really does. I think the reductionist approach has been uh, extremely successful. There's no reason to think that it's lacking anything. There's no emergent phenomenon that I think anyone can say seriously cannot be derived from reductionist principles. Which is going back to what Tim said in terms of like the equations getting simpler. Like we really can think about even that from a reductionist perspective, right? Like you look at the periodic table of elements, and there's like 100 something atoms on there. And sure, if you wanted to describe the universe in terms of those atoms, you would need a whole lot of equations to describe each of those atoms and how they correspond to whatever phenomenon you're trying to describe. But reductionism would, one of the successes of reductionism is the fact that you can actually simplify those 120 equations, whatever, into just like up, down quark, and electron, just like three things. And so I think you can really relate the simplification of the equations into like one-liners from that perspective. And there's no emergent phenomenon that is not predicted by interactions between up-down quarks and electrons. I don't know, Tim, am I wrong about that?
Yeah.
Is there a condensed matter viewpoint that says otherwise?
I, I agree, but I think there are some distinction between what people mean when they ask, oh, does this theory predict X or Y, right? Compared to what a physicist says when a theory predicts something. Like if we come up with a theory of everything that's more detailed, it's not like we're gonna derive psychology from like that theory, right? But it's gonna be able to explain another layer deeper on a theory that seems kind of ad hoc, right? It's probably not gonna provide more information on more emergent phenomenon, right? Like we know how, in principle, we have particle physics that gives rise to atoms, molecules, that gives rise to chemistry, and then that ultimately gives rise to biology and then psychology, right? Like, if we add one layer deeper, it's not going to suddenly create tremendous breakthroughs in the really emergent frontier. Like, that's not going to happen. Let's be real here, right? But it's going to add a little bit more to this chain at the end. It's going to be able to explain things that were previously unexplainable. Maybe like, oh, why is the mass of the electron this way? Maybe we will be able to explain it that way. Why is the way the particle property is this way versus that way? Like, so in a real sense, yeah, we will be able to explain things better in a more simpler way, but it's not going to be like easily translatable to the general public or everyday experiences.
I see. Real quick, can we define what condensed matter physics means? Because we use that term, and I just want to make sure our audience is clear what that means. High level, like one sentence description of it.
I can give it a shot. I mean, condensed matter is just studying the more macroscopic properties of materials, because materials are made of many molecules, right? And a lot of times these molecules are structured in a very structured way in crystals, right, in metal. And then when you arrange these materials in crystals, more interesting property come to be, and sometimes they're kind of unexpected. You wouldn't necessarily see it from the fundamental physics, right? So that's why we say condensed matter physics is kind of like the study of emergent behaviors that you don't get just by studying fundamental physics.
Gotcha. I also want to go magnifying a little bit or double click on that a little bit more of like reductionism and then versus like condensed matter physics. Mike, you seem to mention there was not a dichotomy, but like that they're not really compatible, or I'm not exactly sure what point, but there seems to be like a difference between those two. Can you elucidate that further?
Yeah, no, I think a lot of that was just, like we're from two different camps. And so just like, camp particle physics. But I think the most surprising thing about like condensed matter physics is like, we typically think of like, as a reductionist, like, everything's made from more fundamental constituents. And so we can think of, in some sense, we can think of particle physics as the study of the quote unquote fundamental. And we can think of condensed matter physics as a study of like how the collection of these fundamental things behave. But the most surprising thing, I think, about condensed matter physics is that oftentimes the study of how these collections of quote unquote fundamental things behaves leads you to the realization that collections of things can sometimes be just as fundamental as the fundamental things. And this goes back to this concept of duality that has come up again time and time in physics, where like you can have like, okay, so you can have, a fundamental particle called a quark, right? There's a particle called a meson, which is basically, from a particle physicist would say that's a bound state, a composite particle made up of two quarks. But there is a perspective where you can think about it the opposite, actually, where the meson is fundamental.
Oh, I think you got muted, Mikey.
Yeah.
And that's like one of the biggest mistakes.
Uh, I don't know if I fully caught you, but I'm gonna assume the audience heard it unless like
Oh, did I
this,
break up? I was getting a call at the same time.
Oh,
oh, okay.
yeah.
Oh, okay.
I think
Yeah.
you mentioned this alternative perspective where the meson is kind, you can think of it as more fundamental, and then
Yeah.
kind of it just, it could sometimes break up into other particles, and
Yeah.
that's in some sense a valid perspective on some level. But I want to kind of reiterate back on this kind of difference between condensed matter physics and fundamental physics. Like I think even though the math can be quite similar, I think we follow different principles somewhat, right? In condensed matter physics, you study possibilities. You can study like really interesting phenomenon that you believe lead to really curious looking equations. And you can go to the lab and cook these up. You can be like, hey, I think a material could have this property. Let me really dial it up and kind of make something, beautiful to come out. But I think particle physics is a little different, right? Because fundamentally, the world has been created already. There just is one world. So we can't just be like, hey, we cook up these equations and then we build a different world to test out our equation. No, we can't do that. We have to fundamentally go at it and be like, hey, we believe the world will behave in a certain way. We believe the world has this beautiful, interesting structure, and that's why we cook up equations for it. We can't just be like, oh, I think this equation is interesting. Let's build something like that in the lab. We can't do that. So this is kind of like a little bit of a different perspective and guiding principle when studying these different subjects.
Huh. And then coming back to this, just gonna one last question on this condensed matter thing, and we can move on. If you found a theory of everything from a particle physics point of view, would it be able to explain the properties of these materials that you see? Like
It
that?
probably won't. I mean, the math will get more advanced a little bit, but yeah, but it's not going to help you that much in terms of condensed matter physics.
It could well give great insight into it, though,
It
right? Like
could, yeah.
for example, string theory is probably one of the most promising candidates we have for a theory of everything. Um, and string theory says that if we look closely at each particle, we would see that up quarks, down quarks, electrons, they're really just the same thing. It's just a string vibrating in different ways. If it vibrates this way, it looks like an up quark. If it vibrates that way, it looks like a down quark. Um, and that's kind of the picture. But then actually string theory is kind of like, it also gives rise to this picture that I talked about before, where you can actually think about, a string has two endpoints, and each of those can be viewed as a particle. And so we can actually view that's where this kind of like duality between fundamentalism and compositism, if I can call it that, arises from. It kind of gives a clear picture for why these two things are not necessarily different. If the string shrinks down to a point, you zoom out, it looks like just one particle, but if you zoom into it, it actually looks like two particles attached together by a string. So which picture is more fundamental? String theory kind of tells us that question is moot a little bit.
Hmm. I see. I see. Okay, so it won't be able to help fully with condensed matter, but in the case of this like meson and two quarks, it can shed more light on that.
Yes, yeah, I think it gives more
Yeah.
insight into why these questions are, well, why these distinctions are not that important.
Yeah. But there's no guarantee, I would say. Maybe, but no guarantee.
But there's been a long history of that being true. So physicists, I think, fully expect that with each new discovery, we will get these kinds of kind of unexpected new insights.
Yeah. I guess so. Moving on to a slightly different lens, like looking at through the lens of like language itself. So, in order for me to like write down a theory of everything or anything in physics, I'm constrained to the language of mathematics. And so, how do you know that? Like, I guess there's no way of really knowing, but like, what leads you to believe that like you can write down a theory of everything, knowing that we are constrained by like mathematics itself, like just a language?
I'd say pure faith, just the fact that like, I mean, it's different from the kind of religious faith, but it's the kind of faith that like has been continuously rewarded, over the last 300 years, like almost like in a reliable sense. it might be that we're going to come to the end of the road for this way of thinking. And I think everybody has kind of that sobering thought once in a while. But I mean, hey, it's
And I would add that physics is kind of like there's a bias towards progress, and also I think in order for you to say that, oh, maybe this is a problem, you kind of have to come up with something better, right? Like in some ways this is sort of the best we got. Like the mathematical model, the based on our language, is the best we have, and in order for us to kind of move away from that, and maybe we basically cannot in some ways, right? Like obviously we're humans, like we are constrained by the human condition, um, but that doesn't mean we should just give up. So I think physicists have a tendency to bias toward action, right? Like let's explore and find something interesting to study, and that has rewarded us tremendously so far, I think.
yeah, it could be that we're just, like it could be that we're just monkeys that are constrained by, monkeys are constrained by their inability to speak and discover deeper truths. So that we could be limited by our inability to go beyond mathematics. But
But I don't think that's true. I don't think
I
because
don't think it's true either. But it's especially silly to not try because of a fear that that could be
yeah.
true.
Fair, absolutely fair. I guess so if so now let's kind of venture into speculative territory. Like what do you guys think is like illuminating paths to the theory of everything, like in terms of things you've seen recently, and maybe this just might be the direction, but not quite the theory of everything, but like almost there.
So
Tim, you go first.
yeah, so I would say the theory of everything. Oh, look, like physics ultimately is a experimental discipline. At least, I'm firmly in that camp and believe that we should stick close to experiment. But you can't deny the fact that historically people have come up with models that describe nature, and they were, many years later they were verified to be true. So the theory always precede the experimental verification, right? And part of it is, I believe that the community has a really good way of kind of thinking about intuitions on what is an interesting idea to pursue. And I think in physics, we have kind of honed in on this notion of, structure, interesting structure, beautiful structure, symmetrical structure. That that and time again, it seems that nature has a bias toward these kinds of structure, and I think theoretical physics in general is going toward that direction. They're finding interesting mathematical structure that's really rich, that is really got many symmetrically looking parts, and that are really intriguing and beautiful in some ways. And I think that's, in an abstract way, where the theory of everything is going toward, right?
Yeah. And then one question I had for you, Tim, before we move to Mikey's perspective, is you mentioned there are several examples where like you discovered a theory or invented. I mean, that's a separate question whether discovered or invented, but there's a new theory that came about, it made predictions, and then like years later experiments validated that. Could you give examples of like prominent examples where that appeared?
Yeah, probably one of my favorite examples is the electroweak theory, right? Like when it used to be that electromagnetism, where electricity and magnets seem to be totally different phenomenon from radioactive decay. It seems to be they can't be more different, right? Like look at a fission reactor, right? And you look at that, and how is that related to electricity and magnetism? That seems totally different, right? Like elements change in a weak decay, but in electricity, elements don't change, right? But Steven Weinberg and I'm gonna miss like a lot of, like, is it Glashlow and
Galvan.
yeah, okay, tons of people, terrible at giving credit,
What?
right?
Weinberg et al.
Yeah, Weinberg at all, right? These
Well, if it's
people,
electroweak, it's really mostly Weinberg.
yeah, these people kind of had the imagination to be like, hey, let's put this different forces onto the same footing and in a more symmetrical, more beautiful structure. And this is under the mathematical language of group theory. Think of them as like really intricate geometry, like a cube. You know, there are many corners in the cube, and maybe the different forces are just different facet, different sides of a cube, something like that, right? And they were able to make these predictions that predict hugely different phenomenon. You know, electricity, magnetism, right? And these were years before the experimental validation, where they eventually found the Z boson, the W boson, and these are the equivalent of the particle of light, photons. And when those are discovered, I mean, there's no denying that electricity and the electromagnetism and the weak forces are one and the same thing, and they're unified under like a beautiful structure, and that's why the Nobel Prize was awarded. So that was probably one of the most prominent example in my mind. That beautiful structure leads to progress and leads to actual discovery, and then people anticipated well in advance.
Mm-hmm. That makes sense. I guess Mikey, your turn now.
Yeah, I don't know. I think maybe just going in that same direction. I don't know if it's going in the same direction, but I mean, I am of the opinion, I don't know, that this theory that we call string theory has all the makings of a theory of everything, right? Like in the ways we talked about, it basically unifies all of the kind of disparate phenomenon that we see now under a common umbrella, that every particle is really just different ways of a vibrating string. The problem with string theory, the reason why, in my opinion, it's gotten a lot of unfair criticism, is the fact that it could be thousands of years before we're able to test whether or not this is the right framework. But in terms of like the increase of structure, symmetry, beauty, and also its ability to describe, all of these disparate phenomena that we've talked about right now under a single umbrella. It has all the makings of a theory of everything. It might not be the best language for talking about it. That might be why it's so difficult to solve its equations, get results out of, and make experimental predictions from. But that's not string theory's fault.
Fair enough. Fair enough. I guess then a question I want to pose to either of you is, I remember there have been a few articles or books coming out about like how like the constraint of beauty is like misleading physics, and I'm just curious like what do you guys think about that sort of argument?
Who said that?
I'll have to find it for you, but I remember like that, oh, like physics is like nature might be a lot messier, like why are we seeking beauty all the time?
I mean, it could be certainly that our concept of beauty could be naive. But to say that, I don't know.
I'm
very bothered by this, Mikey.
I think that's a really hard pill to swallow, right? Like, you go into physics, you truly believe that the theory of physics is beautiful. I mean, if you don't think it's beautiful, I think it's your fault, right? Like, nature knows better than you do. So, like, how dare you question nature? I think almost like, in some ways, almost like by definition, the theory of nature is beautiful. And it definitely has structures in it. Like, you can't deny, like, how, how can it be any other way? I suppose you can take this opposite view. You can be like, hey, nature is super messy. But to me, I think personally, this is a negative. It's a negative argument. If you say nature is messy, then so what? Like, what are you gonna do about it? Are you just gonna say nature is just a bunch of random numbers without structure to guide you? Like, that's not very helpful, right? Like, for humans to understand stuff, we get closer and closer to structures, and it seems clear that the more you want to describe, the more structure you require. So inevitably, it seems like there's got to be some logic, some relationship between things, and that, in some ways, will be the definition of beauty, right? Like, these intricate structures is the definition of beauty, I think.
Yeah, that's forgiving, but I think I know who you're talking about, who like says these kind. Oh well, people have been chasing beauty for the last 300 years, but for the last 20 years, they've been stuck. So maybe physics is just messy. Those people have never actually contributed anything to the progress of physics. They're just people who
Well,
look at people. They look at people who are stuck for, and sometimes you get stuck for 20 years. Sometimes you get stuck for 50 years. But the person who's like, well, maybe it's just all wrong, and they don't offer like a better suggestion. I don't know. I wouldn't listen to these people.
yeah,
Yeah.
yeah. I think
We're gonna say something?
yeah, criticism in physics, criticism needs to be constructive. Like physics is very harsh, you know. Sure, like what you get one experiment wrong, your whole thing falls apart. But like before that falls apart, you better offer like a better alternative. Like give me a better thing. Then I'll tell you if you know if that thing works, then your thing is more beautiful. I think that just is true.
It takes zero skill to say, hey, maybe everybody's wrong.
I think that's absolutely fair. Yeah.
Yeah. All right, so we're basically almost at time. I wanted to leave you guys a chance to say any last concluding words before we all head out.
Them
So,
first.
Yeah.
again, Joseph.
Yeah, and I think we can take a lesson from history, right? Like there have been equations that span pages and pages. Probably the most famous one is the Park-Taylor amplitude equation, whatever. That it was a paper and people went through years calculating something, and it was like 5 pages long of equations. No one knows how to simplify it for a long time, and then just a beautiful insight came to be, and then it turns out that many terms cancel, and you just end up with one line. 5 pages got down to one line, right? And it's probably one of the most extreme example of, like the beauty and the structure is out there. It's just waiting for us to discover. Sometimes you literally it's just grab a pen and pencil and just crossing out terms that cancel each other until you get down to one line. And sometimes it's reorganizing existing equation, and sometimes it's viewing these equations in a different lens. But I truly and firmly believe that there is structure out there waiting for us to be discovered, and then I don't think nature will disappoint us, and I think the Holy Grail is out there.
And now you, Mikey.
Yeah.
Is that a real picture behind you? I mean, that's not a fake background, right? Those are the skyscrapers of San Francisco.
Correct. Yeah.
Yeah. I mean, I don't know. Like, I think, like, if we think about like the great advances in theoretical physics, like the very small, tiny consequences of these great advances has been like all of the technology we see around us, and all of that has come from people chasing this je ne sais quoi, like beauty we can't really describe, but I don't know, is it arrogant to say that you kind of know it when you see it? And certainly people have had very wrong definitions of beauty and have gone down wrong directions. But I think so far there's no evidence to me that doesn't vindicate the idea that the deeper theory has some kind of beautiful structure to it. And I mean, we have like everything we see around us comes from this idea. I think it's crazy to abandon it, and I think the idea of chasing this or having faith in this idea that the truth should be beautiful is, I think, one of the highest ideals of like humanity, and we shouldn't just throw it away because some disgruntled person just I don't know wants to write a blog or something.
Yeah.
Well, on that note, I want to thank everybody for joining us, and we'll see you all next week.
Yeah. See you all next week.
Oh.
Bye.
Bye.